So from the example of calculation we've made just before, we will talk about the ring structure of Z over NZ. So as a reminder, perhaps something you don't know for the moment is that the standard set of number you're used to, such as Q or C, actually have a property, and they are so-called fields. That is, for any element, either rational or real or complex number, which is different from zero, there exists some value y such that x times y is equal to 1, and actually y is very often defined or written as 1 over x. That's true in those three sets of number, but not in z over nz. Actually, in z over nz, any element has an opposite for the addition law. That's quite forward, and perhaps I will take an example later to show you how to get an opposite of any element. But only some elements have an inverse. Not all elements have an inverse. That is the definition of a field that's still written on the top left of the board you're looking for. So for any element different from zero, this element has an inverse. Actually, this property is not true in Z over NZ. So Z over NZ is not a field, it's called a ring. It's an algebraic structure where the rule of having an element for any, having an inverse, sorry, for any element different from zero is not true. So that's not really a problem at the moment. You know which elements have an inverse and which have not. And actually, the elements which don't have an inverse are the divisors of zero. So let's remember the latest example. In Z over 18Z, 4 bar is a divisor of 0 bar. So 4 bar doesn't have an inverse in Z over 18Z, because actually there's a relation between 4 in 4 bar and the value of n, which is here 18. Always in Z over 18Z, we made this calculation. 7 bar times 13 bar is equal to 1 bar. So 7 bar and 13 bar are inverses, one of each other. So 7 bar has an inverse in Z over 18Z. So can we go a little further and try to find some general rule that would only depend on n and avoiding making calculations or multiple try to know if an element has an inverse or not? Actually, there is a quite simple rule, which is the following. In Z over NZ, an element A bar as an inverse is equivalent to the fact that the GCD of A and N is equal to 1. So let's write it with the GCD notation. GCD of A and N is equal to 1. That's the way one can quickly determine if an element has an inverse in Z over NZ. And this is, let's say, quite simple to do, especially with little values from n such as the one we've used in the previous example. So let's apply it and check with examples we've already seen. The question is, as an example, does 4 bar have an inverse in Z over 18Z? We already know that this is false, but let's check with the property that I've just shown you just above. Actually, the GCD of 4 and 18 is equal to 2. So, as it's not equal to 1, the answer is no. 4 bar has no inverse in Z over 18Z. Let's check another value we don't see for the moment. Does 11 bar have an inverse in Z over 18Z? In order to answer to that question, we must find the GCD of 11 and 18. Actually, the GCD is equal to 1. So the answer is yes. 11 bar has an inverse in Z over 18Z. So this doesn't tell us what the inverse is. We'll see in a few moments how can one calculate the inverse of an element in Z over NZ using the extended Euclid algorithm we already know. But for the moment, remember that depending on the value of n in Z over NZ, some elements have an inverse, some other don't have an inverse. So in order to know if an element has an inverse or not, just compute the GCD of this element and the value of n to get the answer.